Well, anyway, just to wrap this up, while you were gone, I'm starting to, I put this into Desmos.
Okay.
Right? And I put it into, when it comes up, you're gonna see that this part's gonna look kind of funny, right? I was trying the semifactorial in Desmos, it doesn't understand it.
Okay.
It doesn't know that it's semifactorial. So I had to just put it, but notice this is a product. So I'm gonna use the pi notation as opposed to sigma notation.
Okay.
Sigma notation is used for a sum. The pi notation is used for a product.
Okay.
So right here, there it is. So what we got here, well, you can barely see it up there, I guess, is right there. What we've got here, see, is a sum. I just wrote out the first two terms separately.
Okay.
But the rest of them using this product notation, because it's product of all the odds.
Okay.
You know what I mean? And so and you can see it has the same formula like you were describing.
And the pi notation is just some product, or the product of.
Yeah, it's literally just a product. Yeah.
Of the integers.
Could be, whatever formula you want. Yeah. But in this case, you can see how this is stopping at 4. That's how, to the extent that we computed it by hand. And if you, and the graph ends up looking like this, you just go all the way to the 4th degree polynomial. And if I graph, let me see what the graph of the square root function looks like.
Not like that.
No,
Yeah.
To that point, to that, looks similar to that point.
Yeah, somewhat. I'm expecting it to go from like 0 to 2. And you can see how in red it kind of, I guess it sort of follows it for a little while, but
Right.
yeah, it's not a great estimation. But let's see, what if I take this 4 and turn it into a 6, let's say? Or perhaps a 10. Yeah. The radius of convergence might be less than 1. I mean, it does follow pretty closely around here.
Right.
But here it's kind of weird that it's kind of going up like that. That's kind of unexpected. So, yeah, there is a chance I could, it's kind of complicated formula, there's a chance I could have typed something wrong too. But hopefully I didn't. But that's the idea, it's supposed to follow it pretty good. Yeah. All right. Well, anyway, I think if I had more time, I think it would be a great exercise to kind of try the ratio test on that. You know, just to see what the ratio of convergence is. Because now, especially in light of this, because now I'm starting to think maybe the ratio of convergence isn't one. Right? It doesn't look like it is right now. Right? So, anyways, we'll think about that more, but we'll leave it at that. Yeah. Oh, that's what I'm looking for. Right. Identity functions. Yeah. Oh, yeah. This is an interesting. Just as a side thing, kind of a side. We were just talking today about the limit as x goes to 0 for sine of x over x.
Right.
So it was with much effort and excruciating pain. We saw that this was 1. And we even kind of reiterated that argument earlier today. Well, here's something that's kind of cool. Now that we have Taylor series to work with, you'll recall that the sine of x could be rewritten as x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, so on and so forth. We established that the day you were gone.
Okay.
But we did it using the formula that I explained earlier today.
Okay.
So we did it by computing all the derivatives of sine.
You said that in trig 2. And you said that in trig 2.
Who said that?
You did. Yeah. I mean, y'all were talking about this back in the day.
Ah.
Yeah.
Could be, yeah, because we did use Euler's formula
Yeah.
in there without proof. But now we can actually establish that. In fact, yeah, we can do that now, actually. Yeah, but there's a, so we just reviewed the argument for this, relying very heavily on trigonometry.
Right.
But notice, I could just sin x over x. That's just this power series divided by x. And that's just sin x over x would just be this divided by x,
1.
this divided by x,
So x squared.
and this divided by x.
So even number.
Even exponents, but odd factorials in the bottom. So the limit of this function that was pretty challenging to get a handle on could be thought of as the limit of this power series. And if x is close to 0, that's going to be close to 0. That's going to be close to 0. In fact, all these terms are going to be close to 0 except for this one.
1.
So it's 1. Well, that was easy. I didn't even have to use the squeeze theorem. Here's something you've seen from 152 from integral calculus. It's actually been shown that the antiderivative of this cannot be expressed in closed form as a function. Right? Using the techniques that we know from integral calculus, it can't be done. But nonetheless,
I'm sorry, is this the one that goes like, you can do e to 2 to the natural log
e2 to the natural log
x? Well, no, e to the 2 natural log negative x.
You might be thinking of something else.
Yeah. Sorry.
Yeah, this is an important function to use a lot in statistics.
Oh, we went into class, yay.
That is class. Strange.
It is. But it shows up in very frequently all the way around this. The so-called normal distribution, the bell-shaped curve, or sometimes called Gauss's curve, named after Carl Gauss. But yeah, when you're collecting data, it tends to concentrate around some central number, be sparse, further away.
That's the same Gauss that did Gauss's laws of natural gases.
Yeah. Gauss did a lot. Yeah. So, and this is this function. That's the graph of this function. So in statistics, you might be interested in finding the area under the curve in this region.
I don't know what statistics.
I'd like to find the area of that region. And actually, we did. You may not remember that we did try to tackle that using Simpson's rule, or the trapezoid rule, point rule, and we had ways breaking up into intervals, being able to find like a pretty good decent estimate of it. And so, but we can also, this is another way to tackle it with Taylor series. Right? I can see. The exponential functions can be expressed in this form. And with that, I can see
This -2.
negative 2x. Negative x squared is what I'm going for. So, I'm doing a substitution, right?
Why you couldn't put 2x? Because isn't all of that squared just like e raised to the -2x? Right?
What? E to the x squared
Yeah.
would be e to the 2x.
Yeah, that's what I'm saying.
Okay.
So
So
it's
e
not-
to the negative x squared is something totally different.
Yeah, why wouldn't it be e to the -2x?
Right. Good question. So, the question is this, I'll restate your question in this form.
Oh, I got it. I just figured it out in my head. Yeah. I just
So-
figured it out.
This notation though is slightly ambiguous, I think. Do we mean this,
Right.
or do you
Or
mean
the parentheses on that?
this?
Yeah. Got it. That's
Right? Pre-calculus says that that's the same thing as e to the 2 times x,
Yeah.
but I can't say the same thing, right?
Sure. I just thought about that.
Yeah. Kind of interesting.
Working on my
Yeah.
way to becoming a genius. You know what I'm saying?
Or an NSR amongst the leches.
So that's 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial. I'll just show one more to convince myself that I can see the pattern. See how the exponent is always twice what you're taking the factorial of.
Good.
And if you want to integrate this from 0 to 1, you can just integrate each of these.
But I don't know how to integrate the.
For now, you just keep doing it until you see the pattern. Right?
Use substitution by parts, not parts.
You substitution.
No. One by parts.
No, these are easy. They're all just power rule.
U du
Yeah, but with the
x d
factorial.
dxx.
We treat the factorial as a constant. Just bring it out of the integrand.
Yeah, it's a constant. Factorial is a constant.
Okay, no problem.
So this would just be x minus x cubed over 3 plus, this is all, and each of these are going to be evaluated at 0 and 1, right? So that's going to go from, so I'll fill that in a second. It's going to go from x to the 5th over 5 times 2 factorial. I'll say times 1 factorial. Minus,
Just go to see pattern.
yeah, that's how it is, right? 7 over 7 times 3 factorial.
I know you know the shortcuts. Just tell me shortcuts.
Keep going to the entire bit.
One.
But these are definite integrals. So each of these does need to be integrated, evaluated at 0 and 1 and subtract. And it's pretty easy. In every place I plug in 0, because the power of x is just going to be 0. Everywhere I place a 1, it's just going to end up being 1 over that constant. So I can now see that the definite goal that I was trying to find was basically the area of this marine region could be evaluated with a series. A series, yeah. That's 1 minus 1 over 3 times 1 factorial. 1 over 3. So about 2/3 so far. Plus 1 over 10, I'll say. That's 5 times 2 factorial. So a little more than 2/3, maybe 7. Minus 1 over 7 times 6.
42.
Yeah. Plus, yeah, because I'm doing arithmetic patterns, we're going to these guys now. It says obscured. 9 times 24. 9 times 25.
126.
Mm-hmm.
126.
Oh, that's pretty fast.
Well, it's 24, right? 180 plus 40, 46.
216.
260?
Yeah, 9 times 24.
I was just thinking in my head, 9 times 25. If I had 9,
Oh, yeah.
if I had 9 quarters,
Oh, yeah,
I
okay.
got 225.
I didn't carry, I'm sorry.
Yeah.
We didn't see 9 goes into that.
So if I stopped right here, right? Well, that should be pretty close. It would be better if I knew how close I was, right? But this should be pretty close, right here,
Oh man, you can do
to the area of this region.
the remainder.
Yeah.
Yeah.
So, you know, in contrast to like, remember we did the Simpsons rule here, where, you know, this is not Simpson's rule at all, but it should give us the same answer, pretty close. I'd be curious as to which one would be less work. You do want to choose the one that's less work, right?
Right.
So, yeah.
I want to choose the one that's easier to understand, not necessarily less work.
Yeah, that too.
Less one.
Anyway, that's
He doesn't understand.
So yeah, so I don't know. I think 6.4 is kind of a fun section in a sense, but just because you're just doing all the applications of power series, you know, things like this, things like that, right? Lots of uses of. We also get the binomial theorem from there, right?